have a visitor here. Mr. Romero is here. He missed so much the university that he couldn't stand at home, so he is here. He's wearing mask, so there is no problem. Okay, people, we're going to continue with our example. Unfortunately, it appears the whole thing, but the idea was that you could see only part of this. Okay, so first, as I said before, the cut is here. So this is the sector that we're analyzing. And I'm showing you, since we are in the upper side of the section, the Y average is positive. The V, the shear force, is also positive. So this imbalance, axial imbalance force, is also positive, right? So on the lower part of this, on this cut, okay, we're going to have a shear stress which points in that direction. Okay? And that's what we can calculate. So here I have the calculation of the first moment. So this, as you can see here in this diagram, the distance from the neutral axis to the centroid is 6 inches. Okay? So that's this first 6. Okay, that's 6 inches. And then this area, the cross area here, okay, is half the width. The width is 10 divided by 2, that's 5. And the thickness of each one of the boards is 2. So this is the area of the sector. This is Y average. But that gives us 60 inches cubed. Okay? Now, to calculate the shear stress, we need the shear force. We said that we're going to be analyzing on a cut where we have the largest shear stress, which is 1900. So that's 1900. The inertia of the whole section, you can check it. I'm just giving it to you. So it's 1900. This is inches to the 4th. And then we can apply the formulation that we had: shear force, first moment, inertia, and the thickness where we make the cut. The result is 30 inches, pounds per inches squared. And now we're trying to, this is the stress that it's developed in the connection between boards A and B. Now, we want to determine how many nails need in order to support this shear, okay? And for that, let's assume that we know the maximum shear load that a nail can take is 96 inches, okay? So let's suppose that we have a nail here. This is a nail, okay? And we have this nail connecting 2 boards. So this one board points in that direction and the other points in this direction, okay? And the maximum force that this nail can take is 96 inches, and 96 pounds, I'm sorry, okay? Now here, we have calculated the shear stress that is produced in the connection between these 2 boards. Okay, now, this is a situation. Let me go back just a second, please. You see that on the left-hand side, I'm showing you the shear stress, but this shear stress is on the top, on the flange, okay? And now, I'm showing you shear stress on the board B. This is board B, okay? It's the same, but in the opposite direction. Now, this is the distribution of stress, okay? And the value is 30 pounds per inches square. Now, this shear stress has to be overcome, has to be sustained by the nails. And each nail can develop a force of 96 pounds, I'm sorry. So, okay, on the right here, I have, let's suppose that we have these nails separated a distance S, okay? So this distance is this distance here. So what we say is, okay, this shear stress integrated, okay, has to correspond to the maximum force that each nail can sustain, okay? So if we multiply this shear stress, assuming that's something that we mentioned before, assuming that the thickness is small, so there is no variation in the z direction, okay? In that case, it's easy. We multiply an S. We have to assume in this case that S is small, so that the variation in the x direction of this shear stress is small, okay? We can multiply the value of 30 times the thickness and times S, which we do not know. And this force, which is trying to shear the two boards, okay, will be replaced by a nail. That's what we do here. So the force that develops, or the maximum force that can develop in each nail, okay, will be replacing the shear distribution that we originally have. So that's the shear stress times the area. Okay, now S is unknown. That's what we're trying to determine. So we have the maximum shear, I'm sorry, the maximum force that the nail can take. That's 96 inches. That's something that we know. The shear stress that we just calculated, 30 pounds per square inch. And B thickness, which is 2. So we can cancel pounds, 1 inches, and the result is going to be 1.6 inches. It's very small. It's very small. So the 1.6 is about what? 4 centimeters. It's about this. It's not much. So they're very close. And that's because the shear stress is very high. Okay? So that's that. Okay, so if you want to avoid any problems between boards A, which is flat, with board B, which is vertical, right? You don't want them to allow them to slide one over the other. You have to have enough nails. So at least no more, the nails has to be separated no more than 1.6 inches. If you put it, for example, every 2 inches, that means that the force that each nail has to sustain is larger than 96. And it is possible that some of these nails will bend, and there will be some slide of the boards A over the board B, because they are telling us that you cannot apply over the nails a force larger than 96 pounds, I'm sorry. Okay? Is there any questions about this? Yeah, well, this force depends on the characteristics. For example, you want to change, because you're saying that putting one nail every 1.6 inches is just too much, right? So what you can do is you can increase the size of the nail. For example, instead of 3 millimeters, you can use, for example, 4 millimeters in diameter. In that case, is probably the allowable force, which is right now 96, it will probably go up maybe 120 or something like that. And in that case, okay, the spacing will increase. So you can use larger nails, but more separated, okay? So that's an option. Okay, now, so we have, let me go back. We have determined the nails which connect boards A and B, okay? Now, we have another type of connection between boards B and C, okay? You see that board C is also like a flange, but it's not at the top. It's an intermediate position in the height of the section. So connecting boards B and C will have a different value since the shear stress that they have to sustain is different. So let's calculate first the shear stress. Again, let's, this is the board C, this is the board B. Again, we have to integrate from this cut in the connection because that's where we want to calculate the shear stress. And we have to go all the way up to here. Why? Because here, what happens with the shear stress? Ms. Valdez, what happens with the shear stress in this cut? This cut, Ms. Valdez.
Yes, doctor. It's 0.
Exactly. So in the first cut, you are going to calculate the shear stress. In the other cut, on the center line, the shear stress is 0. So you have one equation, and with that equation, you can calculate the one single value of the shear stress. Yes. So that's that. So the area will be slightly different than this one here, and the distance definitely will be also different. Okay. So let's go. This is the one that we are analyzing right now. Okay, so this is the upper flange, this is the neutral axis, and this is the part of the board C that we are analyzing. So we make a cut here, and we go integrate up to here. Why? Because as somebody said, on here, on this side, the shear is 0. Okay, so we have to be very careful with the identification of the properties. The area, how much is going to be the area here? Mr. Vanegas, how much is going to be the area? Mr. Vanegas, the area for this side, for this piece, for this sector? Vanegas is not here.
4 inches square.
How did you calculate that?
2 inches and the bottom and 2 inches.
No, it's not.
6 inches square.
3 times 2.
How did you calculate that?
3 times 2.
Yes, that's correct. We have to be careful, okay? So from here to here, that's 5. Because that's half of the width, which is 10. And the web has a thickness of 2. So the difference is 3. Okay, that's the width. So from here to here, that's 2. So from here to here, that's 3. And the thickness of every board is 2. So the area is going to be 6. And the vertical distance, I'm showing it to you here, it's 2. Do you expect the shear stress in that cut to be larger or smaller? Okay. The cut is a vertical cut, okay? So Okay, this is the cut that we're doing. So this is the cut where we want to calculate the tau in this. Do you expect to be very large or very small value? You expect to be larger or smaller than the previous one? The previous one was 30. Smaller or larger?
Smaller.
Smaller. Why is that? English, why is that? Why do you expect to be smaller?
Because the area is smaller.
Exactly. The
here
first
is
moment is going to be smaller. Yeah. We have to be careful because next I'm going to do another cut and you will see the difference. Okay. It's similar, but it's not the same. Okay. So let's go on. So Q is the height to the centroid is 2. The area, as we said, is 3 times 2. So that's 12 cubic inches for the first moment. And the shear stress is 6. Okay. So that's our formula. That's easy and all of that. Okay. Now, let me insist on this. I'm doing this analysis. So the shear stress is pointing in this direction. That value is 6. Okay, now let's calculate the spacing between nails. And let's suppose that we're going to be using the same nails. Okay, so this is the situation. Okay, originally, this is the board C. Okay, or half the board C. This is board C. So this is the shear stress that we just determined, which is 6. So this is 6 psi. So this is a continuous distribution. But instead of having a continuous contact, okay, we're going to use nails. Okay, so essentially it's the same. So we space the nails every S distance. And what the originally, we have a distribution of 6 psi on this area, separated or defined with the length of S. Instead of that, we're going to replace that with a single nail. So we use the same reasoning and we're assuming that we're using the same capacity or the same nail with the same capacity. The stress is different and the width or the thickness is the same because all the boards have 2 inches thick. And this is the spacing. Okay, so connecting the A and B develops a much larger shear stress. And that's why we need the spacing to be small, 1.6. And in the other connection, you can space, you can locate the nails with a more separated, more space, larger space between them. Why? Because the shear stress that you have to sustain is much smaller. Okay? What would happen if you try to connect port C and D? Mr. Acuña, Miss Acuña. What would happen if you try to connect boards C and D? What do you think? Boards C and D. Acuña, are you there? Have problems? Mr. Chin Chin, what do you say?
We have the same that we have in B and C because are symmetric.
Exactly. So you will need to include the same spacing probably. And what happened with the bottom? With the bottom board, you try to connect it with board B or C or D. What would happen? Well, by symmetry. In this case, you have symmetry because all the geometry is symmetric, and not only that, but also the thicknesses of every element is the same. So the connection between the bottom flange and the boards B or C or B or D, which are vertical, they're going to develop the same shear stress, and so they're going to be required to have the same spacing as the connection between boards A and B. So basically that's the required calculation. Any questions about these, people? This is something that you have to analyze using in your homework, okay? So that's completes the material. So you have all the material to complete the assignment number 2.
Doctor, I have a concern.
Yeah, go on.
When you said at the last part that the shear force is divided by 2 parts, by B and by table of D, so it completes 19 points.
I will cover that in a second.
Okay.
Okay. Okay, now, as a summary, this is what we have. This is what we have. Okay, so let me go back. In here. Okay, so in this cut, okay, in this cut, okay, this is a vertical cut. So in this point, if this is like that, I need a shear, oh shoot. Shear stress pointing upward. And then we will go like that. Okay, so go like that, and we expect this to increase. In this area, or in between boards B and C, this is very interesting. We have to take a quick look at that. So that's that here. Okay. That's, you see that it's pointing to the right. Okay, so here. Because this is the direction of the shear stress. Okay, so here it goes up, and here it goes to the right. Okay, so let's summarize all of that in here. Okay, you see that this arrow points to the right. Okay, so you go like this, then you go to the right and up, and you see that the word continuity makes sense. Remember that the Q is the integral, and it varies continuously. And then you go all the way up that, and then you change sign, because you need to cancel this effect with this effect. And in here, again, you have up, there is a bifurcation, and then you go like that. And you see that this points upward, upward. But here, you have the opposite. Okay, so you have this goes to the left, joins this one here, and goes up. Here you go to the left. The other side, you go like this, like this. And in here, you add, it's like a flow coming from the left, goes up. Then you will go up like this. Okay, now, let's see if we can check equilibrium. So here, this points to the left, this points to the right. Here points to the left, points to the right, points to the right, points to the left, points to the right, and to the left. So you have equilibrium. Now, what happens with the two vertical sides? Yes, we have to integrate on the left web and the right web. Both integrating, they have to recuperate half and half. So you could recuperate the contribution from half of the, or from one web, and that's half of the shear force, and the rest on the other web. But you have to have every time, I mean, you have to think equilibrium all the time, equilibrium, equilibrium. So in this case, you see there is no net force in the Z direction. There is no net force in the X direction. There is no net torsional moment. There is no net moment, bending moment in the Y direction. So there is only two forces, in the vertical direction, shear force, and bending moment in the Z direction. So we're okay. Because of the two internal forces that we need in order to have equilibrium when we have external forces in the Y direction. Ms. Santos? Okay, before we go on, let me raise a little bit this because in here, this is a sketch of the distribution of shear stress, okay? So in this direction, okay, on the vertical side, in this direction, I have tau xy. On the flanges, in the vertical direction, I plot xz. So on the upper flange, on the two intermediate, and in the lower flange, I have tau xz. On the web, I have tau xy. Okay? Now, if I draw, I make a cut here, okay? That's a cut here. We know that we have the largest value of the first moment. So if we have the largest value of first moment, we're going to have the largest value of shear flow. And depending on the thickness, probably we'll have the largest value of shear stress. So you see that you have the largest value of the whole distribution. And then we go, you see that this is a quadratic distribution. So that depends on minus y squared, right? Here, we have a jump. Why? Because if we make a cut here, we include this area and this area. If we make a cut here, let me change color. You make a cut here, you have to include this area, this area. Okay, so the value that you see here, this value here, is a value that when we make this cut. So we have to consider the intermediate flange, the upper flange in the piece of the web. If we make the other cut, let me change color. This cut here, then this is the value that we're going to go. Because from here, I do not include this, the intermediate flange, only the same piece of the web and the upper flange. So there is a difference. Now, if you plot not the shear stress, but the shear flow, then you will have continuity. That means that this value here is going to be equal to this value plus this value here. That's the reason people call it shear flow. Because when you integrate, okay, you can split the areas of integration. So you consider one side, you consider the other side, but when you consider both, you simply have to add them up. So it's like having a pipe and it breaks. But the flow from each one of them has to add the flow in the incoming pipe. Okay? And then in each one of the flanges, okay, we know that the Y is constant. So the only variation is in area. And the area varies linearly with the length of the sector. So that's a linear variation. And that's what we see, that we have linear variation of shear stress here and also linear variation of stress here. If we go on in the upper direction, we can see that we have a web, and every time we see a vertical element, the variation is quadratic. That's what you're seeing here. This is a quadratic variation. Okay? I don't know if we have any questions, people.
Yes, doctor. I had the question.
Go
Carranza,
on.
what is the different distribution shear stress in the rectangular section with the double bottom and include two longitudinal bulkheads in the side?
When we have longitudinal bulkheads, we are in trouble. Okay? We are only considering sections with no longitudinal bulkheads. Okay, let me open a new second. My screen now, full screen.
Yes, doctor.
Okay. See, what's the problem with a section, for example, a ship section, which has a longitudinal bulkhead? That's quite common, right? The problem is that there is no point where we know the value of the shear stress. That's the problem. Okay, so let's consider a section, simple section like this. It's a barge, and we use a single bulkhead. Okay. Do you know what a bulkhead is? Does everybody know what a bulkhead is?
No.
It's like mamparo.
Right, but in the longitudinal direction. It's like a wall, right? It's a wall that does not allow to pass fluids from one side to the other, but it's located in the longitudinal direction. Okay, we have transverse bulkheads, longitudinal bulkheads. Okay, you have a tank. Probably when you pass they took the stability course. If you have a tank, right, you put liquid. If the ship rolls to one side, heels to one side, the liquid will move. So that will take the center of gravity and we put it on one side. So it increases the inclination, right? So that's what we call the free surface effect. And that depends on the width of the tank, raise it to the third power. So that's why every time we have the opportunity, we have to include longitudinal bulkheads if you are going to transport cargo that can move. Okay, for example, liquids, definitely. Okay, so you use that. And in that case, you will have two tanks, each on one side, but the width of each one of those will be half of the original. Right, so the effect will be 4 times smaller. So it's a large influence. Now, let's go to structures. Here, okay, what do you, let's suppose that we have a positive shear force. Okay, what's going to be the shear stress distribution that we expect? Anybody? Okay, anybody? Let me use, let's suppose that more or less, this is the neutral axis. You see that I put it closer to the bottom. That's typical because usually the thickness at the bottom is higher than the thickness at the deck. So it's a little bit lower, but doesn't matter. Now let's suppose that we have a shear force, positive shear force on this section. What's going to be the distribution of the shear stress on the sides? You think it will point upward or downward? The shear force is positive. So
Upward.
upward. Why? Because when you integrate the shear stress on the vertical elements, you have to recuperate the shear force. And the shear force, since it's positive, this is a positive phase, we have to expect it to be upward, definitely. Okay, so let's put it positive. So we put it positive here. And similarly, because we have symmetry here. What happens in the longitudinal bulkhead? Well, if we have a shear force positive, we expect it to be also pointing upward. Question, can we assume that it is the same as in the sides of the ship? We cannot assume that. So we know that probably will point upward, but we do not know that it is going to be the same as on the sides. So let's put it different. So let's put it larger value just for the sake of this example. Okay, let's go up. So here, you are going to decrease. You're going to the right. Similarly, on the other side, we're going to go up. We're going to the left. This guy here will increase, will decrease, and then what? Is going to the right or to the left? Remember that we have to have null, zero force in the z direction. Because we have only forces in the vertical direction. So what happens is just bifurcates. So a piece goes to the left and the rest goes to the right. So we have something like this and something like that. And now they're going to crash. No, they have to reduce and then change sign. So this one here reduces, this reduces, and here we will have 0 value. The problem is, where is that? I don't know. That's the problem. So we have only one equation for these calculations, and we have 2 unknowns. We do not know where the shear force is null, and we don't know the shear force in the other section where we want to calculate. So that's the problem. So for this type of sections, we have to be patient. At the end of the semester, we're going to review that. So for now, you can consider only situations where using one single equation, you are able to calculate what you want to calculate. For example, can you analyze this situation? Change color. Can you analyze the same section? Now, let's use a hole. Can you analyze that? Mr. Benavides, can you analyze that situation?
We should.
Now, for example, we can make a cut. Let's do several cuts. So let's do a cut here. Okay, so let's include probably about here. We're going to have a neutral axis there. Yeah, we can calculate because the y is going to be constant. The area will vary linearly, so we have a linear variation. Fine, we can do it. If we make a cut on the side, can you calculate the shear stress in that cut? Mr. Cedeño, can you calculate it? We can. Yes. It's going to be a piece of the deck and a piece of the side. The deck, the contribution from the deck will be constant. The contribution from the side will be changing quadratically, but you can calculate it. Okay. Can you calculate the shear stress at the cut, a different cut at C? Yeah, we can calculate it. We take this, we take that, complete, and then we can calculate this part. And for the last part, remember, y average will be negative and the area will change with the distance s. So that's we can do it. Up to here. Now let's go on. Can you calculate the shear stress in this cut? Yeah, because you can integrate from here up to here. The shear stress in this edge is, Mr. Paredes, the shear stress in this edge
Is 0.
Exactly, because it's open. So we can go from cut E until the edge, which is 0. Can you calculate the shear stress at cut F? Let me, where is my pointer? Somebody wrote my pointer. Come on, here it is. Can you calculate it? Yeah, I mean, we have this piece of the deck between the holes, and then the piece of the vertical or the longitudinal bulkhead, which changes quadratically. And you can go down any point that you want. Example, we can calculate here. What happens on the right-hand side? What happens on the right-hand side? It's the same as on the left-hand side. So we can analyze this type of section. See, it has a longitudinal bulkhead, but that doesn't have a closed, what we call a cell. It has it includes a hole. And that's something that we're going to take advantage of, okay, for the calculations. Any questions about these people? Okay, everybody turn on your camera, please. Turn on your camera. I want to see your faces because I would like to know you. Let's see on the left. Mr. Ramirez. Hello, are you there, Mr. Ramirez? Are you there? Mr. Ramirez, hello. Are you there, Mr. Ramirez? That's the problem. See, somebody's there, but it's not there. Okay. Miss Avilés, are you there? Avilés? No. Okay. Mr. Kimi. Hello, Mr. Kimi. Are you in Pozorja?
Yes, doctor.
Mr. Villalba, do you know where Pozorja is? Do you know where Pozorja is?
Yes, I know.
Where is Pozorja? Tell us, where is Pozorja?
Close to Guayaquil.
That's not enough. That's not enough. Miss Acuña, do you know where is Pozorja?
No.
Okay. Please try because ours is such a small country. We should know where all of these places are. Mr. Ortega, Andres Ortega, do you know where Pozorja is?
Morning, doctor. Yes.
Where is it?
In Guayaquil.
No!
Doctor, and
Yeah.
sorry, I was closing the door. And Pozorja is in Guayaquil.
No!
No,
It's
Parroquia
not,
Morro.
no. How, I mean, if you want to go to Pozorja, what road do you take? Mr. Gomez, what road do you take if you want to go to Pozorja? Mr. Gomez, your microphone is off. How do you go to, I mean, I want to go to Pozorja. Give me instructions to go to Pozorja. What would you tell me?
You have to go to Via La Costa.
There you go. And then you go up to where? To Salinas?
Up to Progreso.
And then
you have to
Playas. And then
you go to Via Data and then you get on Pozorja.
Yeah, that's correct. Thank you. I can go to Pozorja this weekend. Maybe we can get together in Pozorja, right? And we can have a good ceviche there. Okay, people, please, I need evidence that you are taking the Excel module that I asked you to take. Okay, I need evidence of that. Okay. Assignment number 2 is running. And assignment number 2 is due next Thursday. On that day, in the morning, 8 a.m., not 7, 8 a.m., you have to be here and you're going to take the quiz. If you want to take the quiz, you have to have turned in your assignment. If you are not able to complete the assignment, how can you take the quiz? Makes no sense. Makes no sense. So, requirement to take the quiz. You have to give me evidence that you have taken the module on Excel. Second, you have to have turned in assignment number 2. So please start today doing your assignment number 2. Okay? Otherwise, it will be just a waste of time. You have questions? Well, we're here. Isaac is there. Daniela is there. Andy is there. You have office hours. Send us a message. Email. Try to be as clear as possible in your questions. That's all what we can do. Remember, next Thursday, the quiz is closed book. One more time, closed book. Now, there are some basic relationships that you need to remember. If I want you to apply a very difficult relation, I'm going to give it to you. But in general, you should remember the basic being relations. Okay? You always remember that the objective of this class is to analyze. That means that you are responsible for knowing from where these relations come from. And then you're responsible for knowing how to apply them. So I can give you a question. Deduce this. What does this mean? Or something like that. Or I can give you a question. Okay, here is a relation, calculate this or calculate that. Because you are responsible for analyzing this type of problems. So you have to know where, how did you get these relations and how to apply them. Mr. Vasquez, when are you planning to come to Guayaquil next week?
In a bus, doctor.
What day? What day?
Maybe Tuesday, because I have to stay a couple days before the test for practice and study.
Okay.
I have a question about that.
Yeah, go on.
The practice is gonna be Friday or Tuesday too? Or wait.
I don't remember the date, but right now, completing the session, I'm going to assign you, we're going to organize groups, okay? A group of groups, we're going to do it, I think it's, Isaac, are you there, Isaac? Isaac?
Yes, doctor. Yes, doctor.
Do you remember the dates or the days where we are going to doing the lab tests? I think it's Wednesday and Friday, right?
Wednesday and Friday, right?
In the morning.
Yeah.
Okay. If you have problems, especially those who have to travel, coming on Wednesday, okay, let us know so we can put your group on Friday. And those who live in Guayaquil, they will have to come on Wednesday in the morning, okay, to do the lab tests. Also, if you remember that you have to give me a short, very short, very short oral presentation with one of the problems in this assignment. Okay? And all I need, see, more than technical side, I want you to practice your English. The problem is that you are 52, and I cannot let you participate in class because we will have no time for it. That's why I'm doing this. I say I'm going to take maybe 2 or 3 minutes for each one of you. Can you see the amount of time that I have to develop to you people? But anyway, I'm going to spend maybe 2 minutes for each one of you. So I'm going to give you, explain me this, explain me that, explain me this problem, whatever. So you are not going to take PowerPoint. I'm just giving to you something to write, and that's it. So Blackboard, write it, explain it to me. Okay? So we're gonna do, as some people are in the lab, the other groups are with me in the classroom, and I will do this check. Any questions about these people? Any questions? Ms. Dominguez, are you there? Alison Dominguez, are you there?
Yes, I'm here, doctor.
Are you in Guayaquil or somewhere else?
No, in Santo Domingo.
Okay. Oh, let's do something, people. Engineer Isaac, do we have the place where every student lives right now? Do we have the place? Do we know?
No.
Oh, so please, okay. We need to organize in groups, right? Did they do that already or not? No?
No, doctor. No.
Okay, so people, we need you to organize in groups. 4 students per group, because you are a very large class, 4 students per group. In every group, we have to have somebody from outside the city, and there must be a woman in each group. So the idea is that you are able to integrate as a team. And the best practice for that is to work with people from outside your little group of friends. So every group has to have at least one person from outside the city. And every group has to include at least one woman. Okay, try every group not to include more than one woman or more than one person from outside, because otherwise there will be groups with no women or outsiders. Okay, so one woman, 1 outside, and 2 from Guayaquil. So I want you to force to work as a group. And you can immediately see that and you immediately recognize that they pronounce different than we do. So we have to accept that difference. That's part of the experience that we want you to live. Okay? To accept that there are differences, and we have to accept it. Not only that, but we have to accept it, and we go and work as a group. Okay, once you know who are you working with, you have to send that group to Sayo or to Miss Sayo. Okay, she's going to receive the name of the students who form each one of the groups. And then she will assign you a number of the group. Okay, so everybody, there has to be a responsible for each group, and that person will send an email message to Daniela Sayo saying that we are these persons and we're going to be group, and she will assign the number, and you have to identify this from outside the city. Okay? Any questions, people? Any questions? Any questions? Mr. Cedeño, Jerry Cedeño, do you think it's going to be difficult for you to find a group?
No,
Okay,
I don't think so.
good. Mr. Villalba, do you think it's going to be difficult for you to find persons to form or classmates to form a group?
No.
No, don't think. Good. Mr. Llanos, do you think it's going to be difficult for you?
No, doctor. It's okay.
Okay, good. So if there is no difficulty, then you should able to form groups, but with these conditions. Okay, people, I'm really sorry because it took me a couple of minutes because at the beginning of the session, I have these connecting problems. I don't know what's wrong with this, but anyway, finally we were able to solve it. Okay, if there's no more questions, if there are questions, please immediately send an email so we can solve them. But we have to start planning that next week you have to be here. And yeah, I'm really excited about knowing you. Okay, people, see you tomorrow. At what time?
Thank you. Thank you.
At what time? See you tomorrow. What time?
10:30.
10:30. Good. Okay, bye-bye now. You can
Thank
stop
you,
the
Doctor.
recording.